Greetings from the Institute of Corrosion. My name is Dr. Praful Sharma from Institute of Corrosion Midlands branch. I'm the chair of the Midlands branch, and we are hosting this webinar today on an interesting topic around subsea pipeline corrosion inspections. We are very honored to have Neil Covin today with us. And let me quickly brief Neil. First of all, welcome Neil to the session. In this webinar. And Neil Covin have got over 35 years of experience. So this is a lifetime of experience today being discussed. His multiple geographies, multiple continents, multiple sectors in oil and gas and beyond, onshore, offshore, LNG, whatnot, asset integrity, corrosion. So we are very honored to have Neil to hear from you about one part of your project and experience on related to subsea. Over to you.
It's a pleasure, Praful, and thanks for allowing us to give a presentation on one of the subjects which is dear to my heart. One is obviously topside corrosion, but the other one is stepping back to pipelines and developing up NDE systems from R&D in the 80s, 90s, and into the 2000s, and developing up NDT systems as we did for assisting us with subsea inspection, both structural and which was very important, and then obviously onto risers, onto subsea pipelines, onto bundles. So it was just to give an overview of that and what we require also for the future, which I've been pushing some colleagues for some period of time. So in contents, we've covered corrosion threats in coated pipelines, NDT strategies for non-piggable pipelines, some case histories, and then general guidance on API standards, and hopefully, just to invoke some thinking as it is from my side about the path forwards for subsea inspection overall. Here on the right hand side is ultimately where we got to, but from pipeline side we always have resided with coatings. So we've had fusion bonded epoxy as our main corrosion barrier for pipelines. We later both onshore developed and offshore developed 3-layer systems, which was polyethylene, polypropylene, polyurethane systems, which are generally 6 to 10 millimeters in thickness, but always do have a fusion bonded epoxy layer. And then this is one that's dear to my heart, but obviously, we use it for weight coating, for holding pipelines to the seabed and also buried pipelines to the seabed, which was a generation we did in the North Sea and worldwide, and particularly used for deep water pipelines laid on the seabed, is cement cladding. So this is the one where we need more work from the NDE side in the future. If I shift to the picture on the right and the techniques, we developed all our subsea inspection techniques from topside equipment. So we had, percentage UT. Some people may not or may realize if they've utilized it, but we did use radiography a fair bit as well, early days in the 80s, 90s for subsea. Long range UT, we've had in sections and developed up equipment, Pulsed Eddy Current, Eddy Current itself, and then alternating current field measurement, which is a technique of eddy current. But if I reside on that just for a second, this is really where we started to push subsea inspection, because we used to use ACFM as we did radiography for checking structures and members structurally for weld fatigue cracking with ACFM, and the same goes for using basically sources. So we used to use radiation sources for flooded member detection, and we still do today. And then what we developed topside for thermography, which was a very useful tool for inspection, say, of CUI, early days with me, particularly for FPSOs. We have had one or two companies that have done development of thermography now, and we've tended to use it for inspecting the internals of bundles, and to some degree pipelines. But overall, there's no specific advancements as such. You've always got to, in my view, review the coatings on the pipeline or the structure and the condition of them and the way we may or may not have to take them off. So early doors with definitely automated UT, we had to remove coatings off pipelines, and that's still very common today. I've got projects on the go the last 2-3 years, particularly in the Gulf in shallow water, 30-40 meters. Our colleagues there will recognize that we tend to do samples of 3-meter sections of pipe, remove the coatings, do an RBI of where we expect the damage to be, and basically do a automated UT inspection of the line, and then reseal the area mainly with sheeting, PVC or polyprop sheeting, and generally the frequency of doing that for inspection is 5 years. If I step back a little bit, the problem we've always had is been basically monitoring non-pickable pipelines. So we've always had the corrosion management side. The primary drivers was with percentage of CO2, H2S scales, deposits in the lines. My favorite, and one which is always a real high risk threat, is microbial induced corrosion, particularly in carbon steels. And I've had numerous instances where this has become an issue on pipelines with anaerobic and aerobic bacteria on risers which have been under insulation in particular. So we've had issues with finding that type of corrosion as such. Then we move on to obviously the alloys, which are more prone to obviously cracking defects at operating temperatures in this range, 40 to 120. So we have had instances where that became an issue with us in the 90s, in particular with development of alloy pipelines that I remember for Norway. So we had a lot of 13 chrome, 15 chrome, 16 chrome that we analysed at one time for pipelines, and we had major cracking issues after 3 or 4 years of development there as we moved into the higher grades back into the 90s, because very few super duplexes and duplexes were used in topsides design or process design, but we did use them extensively for downhole for H2S fields, and then we utilized them mainly in high-class pipelines. And our first experience with that was mainly more so Norway, in deeper water for Norway, that we tended to utilize that. So as I've said, early inspections were limited to partial UT with sampling boxes of about 3 meters long. And we tended to do that for very serious pipelines where we had threats raised and we wanted to do investigation. That was the only way we could actually do it back at that time frame. and we still use that today. Just to turn my attention to this piece of equipment, obviously it's a deployed inspection unit which rotates completely around the pipe. So this is very common design for pulsed eddy current, or even what I called acoustic resonance, which is a type of UT that we use, which is very similar to pulsed eddy current, but uses UT. This is the one that I've just mentioned, which is acoustic resonance technology. So the beauty with this is the factor that it can be used for, defining wall thickness, but it's quite flexible for going through coatings. So it's very proficient at going through coatings. But where my R&D has kind of got to at this phase in time is we're still trying to develop it for cement. So it's a good technique for going through, say, 3-layer coatings or FBE, but we've struggled with it for defining through cement, whereas I've sat a long time developing up systems for basically eddy current or pulsed eddy current, and we need to continue with that. So this here is just a summation of the corrosion side of the threats that we've had. Coating characteristics that we've had is cement cladding, which is the weak one to inspect externally as a screening device, which we still really need to push, is can be as much as 20 to 50 millimeters thick. And insulation layers can be 4 to 6 inches on pipelines. So we've struggled to obviously find a absolute technique for being able to develop through coatings of that thickness, apart from using pulsed eddy current to date, up to 200 millimeters through insulation and cement. But I would have to say we're still developing what I call high frequency probes, because of the cement characteristics, where you lose some attenuation because you've got steel cages for assisting for laying again the cement when the pipe is made with end to end with weight coating added to it after the FBE. So acoustic resonance technology is good, as I've said, for FBE and for polymer coatings, but we're still struggling with cement. Eddy current inspection, that is very good for utilized across welds in particular on pipelines, and we've had lots of success with that, deployed by divers as well as for structure, also for pipelines, and deployed by ROV as well, because divers tend to work up to, say, 34, 36 meters depth, depending on the equipment that they've got subsea wise. The deepest I've ever dived with a diver is kind of 40 meters, not any deeper than that. And then really we're really utilizing robotics, ROVs, and we still need to advance radiography, which we've kind of pushed back into the past a little bit, and thermography can still advance. So the advantage of what we're trying to basically do subsea wise into the future is definitely wall screen thickness screening without taking the coatings off, which is a risk to CP. It's a risk to damaging the pipeline. It's a risk to damaging the wall, and it's a risk to the time frame that we spend subsea doing operations. So if I just talk through the timelines a little bit, as we've listed this as case histories without mentioning any too many names, but this is a big function with me for the last 10, 15 years, is that Exxon and Petrobras in Brazil have had a specific project where they've taken quite a few numbers of specifications of subsea NDE equipment and automated NDE equipment. They've analysed it on flexibles because that's their biggest weakness in 10,000 feet of water, is the defects that they get with flexibles flooding, and also with installation problems, and also with fatigue during storms. And they've been at this for over 10 years, where they've analysed varying UT tools going into high frequency UT, which I've always found interesting because, again, UT for me, the power side of ultrasound is always going to find difficulties in going through coatings. That will always be the same, whether it be topside and transferring it to subsea. But acoustic resonance is one area of technique which is different, with frequency modulators that we've managed to go through coatings and FPE and polymers. But the kind of jury is still out about its efficiency with varying pieces of equipment. Eddy Current, we've had a lot of success with, again, with deep water flexibles, and I know they've had a lot of success with PEC and radiography, utilizing it on samples of flexibles, both in Brazil and samples that they've made where they've done brand new build flexibles, analyzed them, and then taken out flexibles which are 6 years, 10 years, 2 years old, and then tried to do a comparator with the defects as a screening device that they're actually found in. So this project here has always interested me to find more data about it, and it's quite a closed shop. But now and again, I got colleagues who are developing up, PEC or Eddy Current, that will tell me about, their success rate with what they've been doing in Brazil, and it's still a growing market for subsea. So that time frame was about 2009, 2010. I was involved in a lot of development of pulsed eddy current magnets then for flexibles that I could use on my own sites offshore Aberdeen, and we were doing quite automated ring driver type units, which we used on caissons and utilities caissons, which we had a lot of cracking defects with, particularly seawater lift caissons. We found PEC tools very useful for with a driver for driving up and down caissons using rope access people, rather than having to utilize ROVs. We could automate it with a motor and drive it up and down a caisson and get the relevant inspection that we needed to know for the lifespan for that caisson. We've had, development of automated UT crawlers, PEC and eddy current and acoustic array has, been ongoing since about 2005. So it's still quite recent. Thermography came in the last 7 to 10 years. I've utilized it and come across it being utilized because it was a very good tool for us for bundles, for easy installation, where you would have gas line, oil line, injection lines, and control bundles going through a pipe section which could be as big as 42-inch. And no way of inspecting that, but thermography at least could use thermal imaging to actually review through the piping and see cross sections. We've had the development of scanning tools to find screen the pipelines and defects below coatings. So that's basically what we're asking to be done. And the further investigation of pulsed eddy current, eddy current, and I keep mentioning these because we have so much data on piggable pipelines, the percentage that is piggable, and therefore, we can, with eddy current and pulsed eddy current, we need to develop this further, as well as ART, particularly for non-piggable pipelines, which leads me into the statement here, where I can basically state, during my operations lifetime, worldwide, 80% of process pipelines are non-piggable, which is a massive number, both onshore and offshore. That figure kind of resonates with me. Only 15% of pipelines that I've operated with tend to be piggable or designed for pig traps, both using topside facilities, pig traps, through to other facilities infield, or back to site operations, be it a gas oil separation plant or an LNG facility, or oil and gas onshore facilities. So we've only had piggable pipelines about 15%. And when we come into problems where we've defined problems with pipelines, we've tended to move also to changing engineering change methods. So trying to build a new pig trap subsea, or most common that I've come across is Middle East, where on unmanned facilities will basically put on a pig trap and redefine the piping so that we can make it piggable back to the process operations facilities. This table here is basically one of the things that is a driver for why we need some kind of screening equipment for subsea to be advanced further. People get into a lot of discussions with me about, what define the crack size or whatever, but the point that we're really after is inspection equipment that's reliable to define defects, and then we can assess really, through 579 and through calculations, the timeline, what we want to do with that defect, or do we want to uncover the pipeline completely? Do we want to clamp it? If the defect is definitely at the 80% wall loss range, or assess it, or even take it out of service and replace a section. The international guidance has kind of stepped forward a little bit. So recently I was doing a lot of reading on that. This is where it grew with us, was part of the key performance 3 indicators in 2005, 6, 7, and 2009 onwards, with the safety executive in the UK. They were asking a lot of operators about what we were going to do with older facilities and how we were going to manage them, which we ended up developing. Riser integrity management was very focused with us at that time, so we developed the NVRP 206 document from quite a few operators, discussing the techniques of RBI and how we wanted to inspect risers, including, unmanned collet inspection equipment and rope access, and the frequencies we wanted to do that, under 2 years or 2 to 3 years for risers we had issues with. And then it's advanced to a guidework framework document, which is this DNV technical report. So one of the things I'll do with the Institute is recommend this report number to read it, which again is guidance, and also, 571 is a crux with me, because it's been the baseline for us for doing topsides inspection and developing up the techniques, because all the techniques that we use subsea, we have utilized them topside previously, and then pushed equipment manufacturers, 2 or 3 that come to mind, with regards to pulsed eddy current and eddy current equipment, and now acoustic resonance. These 2 or 3 suppliers have advanced further in development of these pieces of equipment and automated them to go with ROVs. And it leads me into the final understanding realities that we've lived with pipelines is still, our major threat is gas leaks in the North Sea. Our traditional corrosion management inspection techniques has been developed from 571, which is a good API document and gets reviewed quite regularly. So we've advanced it for CUI. I've seen techniques advancing from this now that we utilize for Subsea. And we're still searching for, over the time frame is basically taking things out of service if we're still high risk. But our current practice is still to remove on pipelines at least 3 millimeters of coating after doing an RBI assessment of topography of the line and doing automated UT or automated PEC or even, development of other techniques. So our future needs, and where I've come to the resounding conclusion is still, we still need screening or an automated NDE technique for thicker coatings. We need the high frequency development of probes for pulsed eddy current and eddy current to be developed further into arrays. They are being utilized, but they're only being utilized in certain companies, small companies. And we need, thermography and one of my favorites, which is alternating current field measurement, which we've used for structures for many years, to define obviously wall thickness percentages beyond wells. But anybody that reads equipment scopes for this, it can go down to defects within a plus or minus 0.2 millimeter range. So it's still very effective for a screening tool. Picks up cracks and picks up obviously defects in structure. And this is the big one I looked at over 10 years ago. And if we could develop it further, put it out there as an item request would be, we know we've got pulsed eddy current, and we're dealing high frequency probes for that as an array. But if we had electromagnetic resonance, as per we have in obviously utilizing it for hospital usage for defining layers, if we could have that developed for subsea usage and automated equipment, that would be one of my top of the line list requests into the industry if it was physical to do, because all we're basically doing is taking topside NDE equipment and encapsulating it into pressurized containers, and the probes run automatic driven by an ROV and an umbilical back to surface ships, which they're launched from, to go onto deeper water pipelines up to about 250 meters at the moment. And I would just like to thank everybody for the attention to give me the ability to talk for this period of time, and quite happy to explore any further discussions.
Thank you, Neil. Thank you for excellent presentation, and we are starting to see some question and answers. So with that, let's move to the question and answers, and I encourage all our participants to please post your questions, and we have some good time for that. So let's start with the first question, Neil. I will read it out for you. First of all, Mr. Amr Saleh says that thanks for the excellent presentation. His question is about regarding the PEC, Pulsed Eddy Current. Could you explain more about the technology capability? Can it be used in quantifying and sizing the defect? Is it costly? And I hear that it is a very slow technique. A lot of questions in
Right.
one. Yeah.
Understood. Yeah. As far as slowness, the probes that we're developing today, the high frequency ones, we tend to use them as an array where we'll put them in an array of, say, 3 probes. So the minimum that you'll see on a base plate, which is put into a circular mode around a pipeline, so you clamp it to the pipeline and rotate it, is about 3 probes. You can use more, and therefore scanning around, I'd say to do a 3-meter section of pipeline, it would take a few minutes, depending on what we have done to take the pipeline up from the seabed and hold it. The other beauty that I've found with Pulsed Eddy Current is obviously at least you can see through the pipeline in quadrants. So I can put it on the top of the shell, 180 degrees, and still also be seeing the underside if it's partly buried. So that's an efficiency thing. As far as wall thickness is concerned, I've never had too many issues with it. It'll stay within the plus or minus 3% range. UT tends to stay within plus or minus 10% range of wall thickness, and we have magnetic flux leakage, eddy current, and pulsed eddy current. And my experience with them is they tend to stay in the range defining wall thickness to plus or minus 3%. So they are slightly better. Defect management, yeah, they are, depending on topography, you can with, say, ACFM usage in the past, if there's a lot of corrosion there, it can get a bit mixed up. I've also seen that happening with MFL units if they are not running at the right speed across a pipeline. So very similar to scanning techniques subsea, we don't really have that problems. And I would say it is the technique that we probably have the most confidence with going through cement. Whereas I would have to take the cement off if I was using UT, or even to some degree, definitely ACFM. ACFM, depending on the defect sizes, and also acoustic resonance at the moment. I've had success with that with polymers and coatings, but not with cement. So there's only really eddy current and pulsed eddy current, which I feel confident enough with to move forwards, that we could use it as a screening tool across cement up to 3 or 4 inches.
Okay, thanks. Thanks, Neil. And I think Amar Saleh is saying thanks for the explanation. The second question, other question is from Mr. Selva Kumar. He's asking how to assess internal corrosion of a subsea pipelines for non-piggable pipelines.
Yeah, the way we've tended to do that in the industry and the standards that we've got today is we've relied on assessing of the corrosion product coming through the line. We've relied on coupons, both sides of the line, both from the facilities and also from subsea side. So we've had, in the 80s, 90s, we even had array units actually built onto the pipelines, which were corrosion coupons themselves. I remember them going in both in Columbia pipelines, and also we played about with them a fair bit in the 80s, 90s in the North Sea. So we had varying usage of that, and we were basically using ACFM then and corrosion coupons. We've utilized ER probes, etc. But anywhere along the pipeline then where we feel is high risk, what we've tended to do, and it's always been the same, is if we can get to it at depth with an ROV, we will explore and trench out the pipeline. We'll at least trench out about 10 meters. We'll take the coating off of 3 meters and we'll go and inspect that. And because we've had success in taking the coatings off, we've tended to use UT. So the UT arrays we've used is very similar to Pulsed Eddy Current. There've been at least 3 minimum probes, and now we're using, acoustic resonance probes. So although people come at me and talk about acoustic resonance, they will still take cement off and use acoustic resonance on top of the FPE once it's cleaned. And that's why we've tended to do sampling. So it's been sampling that we've done, and the fields that I've had in the past, we've tended to do, say, 5 or 6 areas across a pipeline. It's maybe 6 kilometers to 20 or 30 kilometers. If it's been in the Gulf, for example, which I've more au fait with, that's how we've tended to do it, is do sampling externally.
Okay. So Neil, question from Diego is, have these techniques used in conjunction with ICDA approach to focus inspection activities on specific areas of the pipelines?
As far as standards were concerned, it was always brought about by Subsea RBI that we've utilized on techniques and assessments that we've got from subsea trees. So if we had wells with higher water cut and we've done corrosion rate sampling and assessments, or ER probes, and we were worried about the corrosion rate, we would basically then go in and do, the removal externally of the cement, particularly, or utilize ACFM and basically radiography. Early days we utilized it, sampling, and do it that way. So it was really driven from RBI and submitting to the regulator our condition assessments that we've always done, like pipeline reports. Every 2 years we write a pipeline report. Every year we do assessments, corrosion assessments. So it was driven out of high risk lines that we would go and investigate these items. If I think about pipelines that are piggable, we would, pig them, find defects, and then go in and do sampling externally, even for them. So we would find a major defect, which tend to be in the first 3 to 5 to 7 kilometers from operations facilities with water, gas, oil being shipped. I would tend to find more defects in that area because you would get solids drop out, scale in these areas. So if it was by ILI in the riser or the pipeline, we would tend to investigate them by removing the actual external coatings and still using UT or ACFM as it was at that stage. That's how we would do it, but driven by Subsea RBI and assessment of kind of process conditions changes and subsea well changes conditions as far as production.
Sure, thank you. There's a question from Dr. Vijesh. Is in subsea coated pipelines where carbon dioxide and H2S exposure promotes MIC and condensation effects, how can we reliably differentiate between coating disbondment due to CPO overprotection and underfilm corrosion initiated by MIC during
Okay.
during ND inspections like Pulsed Eddy Current or ACFM?
Okay. So, as far as despondent with CP, if we were getting above 1100 millivolts, it's tended, we tended to find examples in Norway, which was a lot more mass of aluminium for seawater protection. So it's a fascinating subject, which has always fascinated me because of the voltage conditions. Because if I go to a laboratory and do tests on despondent coatings, the tests that I've done on despondent coatings in a laboratory in the 80s, 90s, and continually, both to varying specifications, but particularly ELF1, we were up at 1.4, 1.5 volts before we could get despondent of the coating, FBE and PVC or polypropylene. So we were at quite a high voltage, and therefore the safety factor has always been 1100 millivolts. As far as inspection, you would pick this up by the ROV surveys, utilizing the basically monitoring devices for CP to see in the range. So areas where they were above the range, etc., we would probably go and re-inspect if I get the question right, and see if there's a definition. Coupled that with obviously monitoring of CP, we can define by attenuation, which is my favorite, by attenuation examples software, we can define the differences with coatings as it is with finding areas in the pipeline where we feel there's MIC, which is more likely to be in the bottom of the pipeline for sure. So by my experience, I've very, very rarely, apart from I think one gas wet vapor pipeline, ever come across MIC being an issue top of line. Maybe there's some experience out there which is different, but with CP, if I monitor it by ROV and what we got by basically attenuation data by the ROV CP management, I can define the differences between coatings and internal corrosion.
Great, thank you. I think the another question is from Ali, who is asking about which technique is the most cost effective. I'm presuming it's for subsea inspections.
Yeah, the one that I've found the most cost effective over my time frame in the industry is definitely ACFM, which we still utilize today because you can use that on structure, you can use that on pipelines, and then subsea wise, if I talk about pricing, well, an average vessel for inspection in the North Sea would be 250 to 250,000 pounds a day, and then you've got to tool it up with maybe a specific ROV, and then go and lease, personnel and NDT personnel to look after and mobilize and attach their inspection equipment. So subsea wise, the biggest cost is obviously the vessel and staying on station. So obviously it's got to have basically all the thrusters in place to be able to maneuver around a pipeline. ROV package that you have if it's a work class, and a lot of it depends on the depth we're working in. So we're all comfortable up to say 150, 250 meters, and then after that, I've never worked other than a high class ROV, which can go any deeper. And that's the other question mark, is how deep we can go with some of these inspection techniques. Right now, we're sitting at about 250 meters as such, which is why Petrobras and Exxon do tend to pick up some of their flexibles and bring them topside to have them re-inspectable on onshore. And they do that on a set frequency because of fatigue. So they can only inspect so much of it in water up to 150 meters. And then after that, generally, deep water flexibles is problematic to inspect. So cost-wise, yeah, it depends on the equipment, but I would plumb for Pulsed Eddy Current or ACFM would be my two favorites.
Great. Thank you, Neil. And I think that's the end of the questions which we had. A lot of good questions, and I would be willing to give the mic to actually one or two participants who maybe, because we have some time, maybe 5 or 10 more minutes. So maybe uh, s- uh, someone in the audience wants to ask some questions or interact, we have a space for, just raise your hand, click on the raise hand button, and I'll if you're willing, and probably you can ask the question directly as well to Neil. I mean, this is the experiment I'm doing. I've never done this before, but because we have time today, a few more minutes, let's see if it works. So please feel free to raise your hand, and I'll give the mic, and then you can speak as well. Let's see if we have some questions. Otherwise, you might have answered all the questions, Neil. So while we are waiting for that, I have one question, Neil.
Yeah,
I was just prioritizing every, from the audience.
yeah,
But I did have a question. So imagine this, if I presume there's a difference between the crude oil pipes and the gas pipes, and then there's a
yeah,
multi-phase pipes.
yeah.
Do you see from the subsea point of view, many times there's a separation? The transportation is after the separation of oil
y-
or gas, or
Absolutely. Yeah,
many times it is not
it's
separated. So do you see
correct.
do
It's
you,
it's down as facilities have got older, pre-fell, we've come into longer risk, So I define it as two things. In subsea side, we need process stream and process systems. So we've needed jackets. So our biggest weakness in the North Sea has always been fatigue and managing that. So in my generation in 2006, people came on us and said, how can we divine or redefine design life when we've gone past 30, 40 years and we're there now? And my only question is, well, you have to do a lot of analysis and then go and actually inspect the structure. So that's the one area. But in pipelines, my present experience has always been, you get three-phase production separation. If the separation is not very good and we start to get more than 5-10% water going down the pipeline, it will tend to settle out depending on velocity below a meter per second within the first 3 to 5 kilometers. And in my time frame, I haven't done it touch wood, but I've had two colleagues in the past that have replaced pipelines, which I felt we could have clamped. Um, and they've done that in the North Sea on two occasions. So it depends on the product line and CO2 H2S as a threat level. But our threat level still is obviously gas lines, because what's always scared me with gas lines is losing a riser under a facility. And therefore, you're wholly dependent then on infrared and sniffer systems picking up that gas volume in and around the structure and the seabed, coming up through the actual structure itself. So thankfully, I don't hear too much of that happening. Um, but yeah, it just depends on the phases and inhibition. We probably, advance inhibition a fair bit more. The pipelines that I would really risk the most or really worry about, I would definitely put them down for change management so that we put in a pigging system.
right?
And that then just comes down to economics, doesn't it? You know what I mean? Where, a lot of gas lines don't have pigging systems
Yeah.
and not so much oil pipelines do either, apart from export ones. But the ones that I've looked after that are with pigging systems are pigged every 2 weeks or every 4 weeks. And it's them that we've got through 40, 45 years. Like if I look at the Claymore pipe system to Flotter, and then slightly I can say, in the last 10 years, people have poured more and more water into that past the scope that was ever written for them, which is 5%. So quite amazingly, I'm shocked that certain export pipelines are now being used as what I call a flow line. and I treat them totally different as far as RBI and inspection. So that is the concern for an aging asset. If we look at the North Sea compared to other areas, and then
Right.
back on RBI, it's gas. Gas
Okay.
lines. You want to make sure, particularly the risers, that you keep them in inspection focus.
Okay. Thanks. We have a question coming from Muhammad Usman. Actually, you have written the question about ILI, but I also, Mohammed, if you want to talk and speak directly, you can unmute your button and you can talk and ask directly. We are experimenting here, but
No problem.
if you want to do that, Mohammed, you can ask directly to Neil. Do you want to speak? Otherwise, I can read it out as well. Okay, so I mean, let me read it out in this case. So, crack detection ILI tools are notoriously complex
Yeah,
and have higher uncertainty than metal loss tools.
yeah,
So, for subsea pipelines, what are the current POD and sizing accuracy for SCC and fatigue cracks? And what operational factors like product batching, flow velocity most significantly impact the performance of these tools?
yeah. All my time with Tuboscope, we had a rule of thumb that basically, in the 80s, 90s, in our big contract that we had with Aramco, and presently I don't know if they still hold it today, but our tools were developed about a magnetics package which we developed up in Seller, and these tools were good for proficiency of uh, creating the right magnetic field through the pipe. And if I put it that back in the day, and I think it still stays today, the most we can magnetize a pipe at the right speed for the weighted tool is about 1.25 inches. So 1.25 inch wall thickness we're comfortable with, and we're comfortable with a speed back in my day was 3 to 5 meters per second. Now, because of drive units and magnetizing high resolution sensors, we've been able to get it to a meter per second or below. So the efficiency depends on the velocity and the magnetic strength, field strength that these tools utilize, which we build in the workshop. We've got test loop pipelines we've developed them with around the world. There is one here in Scotland. There was one in America I used to utilize as well for developing the tool strength up. Then they come in ranges. So the most common pipeline range is basically 24 inch. So we have magnetic packages for 24 inch pipelines, which is the most common around the world, up to 32, 42, and then downwards to 12 inch, 14 inch, 12 inch, 6 inch, and then they're split up into ranges amongst varying companies. But Germany tended to take over, and Holland, as specialties in magnetic packages and particularly magnetic resonance. So the speed of the tool going through the line is critical. I've had a lot of problems with them dropping through risers because you've got to realize the weight of these tools is generally a 10.5 to 2 tons. If you're talking about a 24 inch ILI tool, it's sitting at around about nearly 2 tons in weight. So dropping it through gravity, she picks up velocity. So staying within that range and control is important. Uh, Probability of detection, it's always been by design. So writing specifications for oil companies and with ILI companies, we've always resided at probability of detection of 90%. So if the tool is utilized and magnetic tape and data taken with them, then the probability of detection of all defects is still within 90%, which leads me to 10% of defects which we miss. So I've had 3 instances where defects have been 1 to 2 millimeters in diametric size, no bigger than 3, and a cluster maybe of them because of MIC as it was externally. It was aerobic MIC, and the depth of it was 6 to 7 to nearly 8 millimeters, and it was a cluster. And I've had MFL tools on 2 occasions miss these kind of defects. I've had to go in, strip the riser, and find them with practical UT, which one of them was a 45-year-old 8-inch line. It was a very small ball line. And she holed on me, but it was basically pressure below 3.5 bar. That we found that defect. So there is, instances where you will miss defects with MFL. And I take your point on crack tools. In my time in the industry, everybody's pushed and advanced them. So, we've had to go with MFL, people talking about, high resolution UT tools. I am coming across now people using, because they are already using acoustic resonance, which can pick up these kind of defects. And it's hard to define them, be it whether they were manufacturing or, installation issues, or they've happened actually in service, which you can maybe define by where it is in the positioning around the cylinder of a pipeline. So my time in reporting generally with oil and gas companies is will reside with MFL, will reside with UT tools, which only have a percentage of the market, maybe 5%. And we're developing up acoustic resonance as tools for larger diameter pipelines, etc. But proficiency in design for detection, it will still reside on the contracts they have with oil and gas, and that will still reside at 90% probability of detection. And I think that comes out of, +5, -5, or +10, -10 when it comes to actual sizing of defects itself. I've got a standard which I refer to, so I can detail that out and pass that on to Profel and pass it to you. Not a problem with that.
Yeah, I mean, if thanks, Neil. And if one of the audience members needs it, they can reach out to us in ICORR, and then we can connect you with Neil and get information if Neil is willing as well. So with that, I would say I think we are reaching to the end of this webinar. I think there was so much of good questions, and some of them, were very, very good technical questions. So that was the intention here. So thanks, Neil, for educating our members and audience on this deep topic of subsea inspections and Eddy. So thanks for coming over and spending time with us.
Not a problem. It's been a pleasure, as it always is with the Institute of Corrosion.
Great.
So dear to my heart.
Thank you. And to the audience, we conclude this webinar just to say that if anybody will need CPD certificates, please email us with this webinar name and your name, full name. We will respond back. And keep watching this page. Please follow our LinkedIn page where we announce new webinars with experts like Neil. And feel free to reach out to us on Midlands branch for any questions if you may have, or any suggestions you may have. With that, thanks everyone. Thanks, Neil, and thanks for the audience for joining. We conclude this webinar.
Thank you.
Have a nice day.
Take care. Have a good evening, everyone.
Thank you.
Take care now.